Towards the end of the previous lecture, we had begun the discussion on the stability aspects of MMIC amplifiers which are non-unilateral. That means for those amplifiers, the S12 is not 0. In that case, we saw that essentially for those amplifiers, we have two kinds of stability criteria. One is the output stability criteria. The other is the input stability criteria. So the criteria for that is to have the gamma in and gamma out to be both less than 1. But to find out whether if an amplifier is potentially unstable after any of the stability tests that we saw in the previous lecture, if a amplifier is potentially unstable, we saw that by judiciously choosing the source impedance or the load impedance, we could make it stable possibly. So to find out what kind of or what governs the choice of those source and load impedances, we said that let us consider the condition for marginal stability. That is when the modulus of the gamma in and the gamma out are both equal to 1. So for output stability, it is gamma in magnitude should be 1, and for input stability, the mod of gamma out should be 1. These are the conditions for marginal stability. So we substituted the formulae for the gamma in and gamma out, which was something like this. This would be 1, and on the input side, this magnitude would be 1. So using some mathematical manipulation, one can isolate the gamma L in this case and gamma S in this case as a separate term, and what is seen is something like this. Just to rearrange the terms and some manipulation further, what is seen is gamma L minus S22 minus delta times S11 conjugate, where delta is the determinant of the S matrix at that frequency of the amplifier, the whole conjugate divided by mod of S22 square minus mod of delta square whole mod is equal to and in this case, if I were to draw a line of separation between these, what we see is mod gamma S minus S11 minus delta times S22 conjugate whole conjugate divided by this quantity, the whole mod would be equal to S12 S21 divided by S22 square minus delta square, the whole mod. So therefore we said that only the gamma L and the gamma S are variables at that frequency. What is fixed is the S parameters, and since delta is also a function of the S matrix, we can consider that also as a constant. So therefore we can assign some names for these, and we'll say that mod of gamma L minus CL, we'll call this as a constant or some complex constant on the load side, and that is equal to some real quantity that also is for the load side, because we are talking of output stability. And here we said that this equation can be called gamma S minus this complex quantity on the source side whose magnitude is equal to some real quantity on the source side. This will be S11. So just be careful with the formula a little bit. So what we said was, since gamma L is a variable over here and gamma S is a variable over here, while CL, RL, CS, RS are constants, if I were to draw the trajectory of this equation as a function of gamma L, I would actually see that these two are circles on the complex gamma planes. So these two are essentially circles on the complex gamma plane. So when you hear about this term called complex gamma plane, intuitively one will think about the Smith chart. And that is true also, because the Smith chart is nothing but the family of circles constructed on the complex gamma plane. So therefore, if I were to draw the complex gamma plane for both output stability and input stability, what I would see is something like this. We will see two circles. One is called as the output stability circle and the other is called the input stability circle. So if I draw the complex gamma plane, let's say this is U, this is JV, this is U, this is JV, except this is the plane for gamma L plane and this is the gamma S plane, because for output stability gamma L is the variable and for input stability gamma S is the variable. So in general the circle might look like this. Here also let us say the circle may look, let us say in general, it may be over here, it could be in any quadrant that we don't know. So the equation where mod gamma L minus CL equals RL indicates a circle with the center as a complex number, that is CL. So the center of the circle would be indicated by a complex quantity, that is CL, and RL is the radius. So therefore if you were to construct the radius, this distance would be RL. Likewise, the input stability circle equation is something like this. So therefore the center of this stability circle would be this complex number which will look like a vector, that is called CS, this point, and the radius of this circle would be RS. All of these quantities are normalized with respect to the gamma L or the gamma S respectively as needed. Now, what information does this convey? The information that these stability circles convey is not yet very clear to us. So therefore, let us go back and ask ourselves, what is the point of doing so much of analysis? The point of doing so much of analysis is for us to find out whether we can judiciously choose a proper load impedance or a proper source impedance so as to ensure that potentially unstable transistors somehow become stable. So therefore, since the question of the choice of source and load impedance arises, we need to also introduce some information in these graphs which talk about impedance. Now, when I immediately say the information of impedance on a complex gamma plane, my mind immediately goes to the Smith chart. So therefore, let us do that. So let us say we have two coordinate systems. This is, let us call this as the gamma L plane. This is the gamma S plane. So as we know, if this is the axis for the gammas, then the Smith chart is a circle of radius of magnitude 1 on this plane and center is on the origin. So therefore, the Smith chart looks something like this. This is the Smith chart. So is this. So all the resistance circles and the reactance circles are inside the Smith chart. Now suppose we draw the stability circles which we had drawn in the previous page, the output stability circle and the input stability circle. Let's draw that. So therefore, this one would look something like this. And the input stability circle might look something like this. Now, this distance is CL and this is RL. This distance is CS and this is RS. We've already discussed that. Now, this circle indicates what? This indicates a circle on the gamma L plane with center CL and radius RL. But how did we arrive at that position? How did we arrive at this circle? We arrived at this circle starting from the condition of marginal stability. Starting from the condition of marginal stability. That is when mod gamma in is equal to 1. When mod gamma in is equal to 1. Similarly, we arrived at this circle, that is a circle on the gamma S plane with center CS and radius RS. We also arrived at this circle by considering the marginal stability on the input side, that is mod gamma out equals 1. And this trajectory indicates just that. The marginal stability in each case. Marginal stability in each case, whether it's input or output. So one thing to note is that you can see in general that the part of the circle is inside the Smith chart and the part of the circle is outside the Smith chart. So it is over here. So is the case. So this is a very general case I am showing. In general, it may also happen that except this specific case which I am showing right now, you may see in general it may so happen that the circles, the Smith chart and the stability circles may not intersect, or one may be inside the other. All things are possible. But let us look at things as they come. One good thing is that we must choose any impedance that must be inside the Smith chart. That is either this area or this area, which is common. We cannot choose anything outside the Smith chart because then that would mean there is negative resistance. Likewise, for the input case, we can choose something over here or we can choose something in this common area. Choose what? Choose the impedance. So, in the gamma L plane, we have to choose ZL, and in the gamma S plane, we have to choose the ZS. Now, we are not sure how to proceed from this point. All we know, let us consider for the time being the output stability circle. The stability circle is over here. The choices for us to choose the impedance is either this larger area of the Smith chart or that part of the Smith chart which is overlapping with the stability circle, that is this smaller region. Definitely these two regions will indicate something. These two regions will indicate something. That is, this circle indicates mod gamma in is equal to what? At whichever point you are on in the stability circle, you will always see that the gamma in is equal to 1. So therefore, if I choose any point which is not on this circle, that would mean that point is gamma in not equal to 1. Suppose I choose a point that is here, I choose a point that is here. I do not know. But one thing I can say is that the gamma in will never be equal to 1 in either of these cases. But what do we want? For stability, we want that gamma in should be less than 1. We want that gamma in should be less than 1. Therefore, one thing I can say for sure, if I am somewhere inside the Smith chart, whether I am in this region or this region, because the circumference of the circle or the arc of the circle, that locus indicates all points where gamma in is equal to 1. One side of the circle will indicate gamma in is less than 1. The other side of the circle will indicate gamma in is more than 1. We do not know which is which. So let us say it may be possible that this part of the Smith chart may indicate gamma in is less than 1, whereas this part may be gamma in is more than 1. The converse can also happen. Here gamma in could be less than 1, here gamma in could be more than 1. We do not know. So how do we know that? What is gamma in? Gamma in is S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L. We have to ensure that this quantity should be below 1. The modulus of this quantity. So now we are in a fix. We do not know which region to choose. So therefore, let us make things simple. So we'll say let gamma L be equal to 0. Let gamma L be equal to 0. Which point is that? That point is right at the center of the Smith chart, which indicates a match load. So if gamma L is 0, that means gamma in is equal to exactly S11. By choosing gamma n equal to 0, I can immediately know what will be gamma n just by looking at the S11. So if S11 is less than 1, my gamma n will be less than 1 also. So therefore, this point will indicate a stable point. So I'll say if S11 is less than 1, then the gamma L equal to 0 indicates a stable point. So therefore, I can choose any point inside the Smith chart that is on this side of my stability circle. Because now I know this point, because this point on this side of the circle indicates a stable point, this entire region would be stable. And anything on this side of the circle that is inside the stability circle would be an unstable point. So therefore, I will shade this region and I will call this as the stable region. Means you are now free to choose any load impedance that is in this region. Means you can also choose a match load point if you want, which is fine. Now if you do the opposite, if this is the stable region, then let me then draw a different shade over here. This is the unstable region. So do not choose any load impedance over here. Right? So what if we look at the other way around? What if we look at the other way around? That is, if the output stability circle looks like this. This is the Smith chart. This is the stability circle. Again, if now the magnitude of S11 is more than 1, which is possible for an MMIC, then what? Again, choose gamma L equal to 0 point. That is the center of the Smith chart. Then, if gamma L equal to 0, gamma in will be S11, which is more than 1 in magnitude. Because S11 is more than 1, so therefore even gamma in will be more than 1. So therefore, this point would now indicate a point where the gamma in would be more than 1. So therefore, this is what we don't want. Now this trajectory still indicates gamma in mod is equal to 1. So therefore, this region would indicate the point where gamma in is less than 1. This is the stable region. And this entire thing this is the unstable region. Similar is the case for the source impedance side also, because gamma in will get replaced by gamma out and S11 will get replaced by S22. So therefore, let us pictorially draw what we have learned so far. Let us represent it through some drawings. analysis of stability circles. Let us consider first output stability. Then we'll go for input stability. Let us consider some cases. Let's say case 1 and case 2. This is the Smith chart. SC means Smith chart. This is also Smith chart. And the stability circle looks like this. So case 1, let us take the mod of S11 is less than 1. In that case, the stable region is this. ZL can be anywhere in this point. In case 2, if now mod of S11 is more than 1, then this will be the stable region. Let's draw for input stability. Again, we'll take two cases. One where mod of S22 now will be less than 1. This is the Smith chart. Case 2 is when S22 is more than 1. Suppose, let us say the circle is over here. This is stability circle. So if S22 is now less than 1, that means if we take gamma S equal to 0 point, that would ensure that that point would correspond to gamma out being less than 1 also. So therefore now this will be the stable region. But if S22 magnitude is more than 1, the stable region would move to this point. This is how to work with the stability circles or understand what the stability circle indicates and what information it is trying to give out. Let us take a look at this in little more detail. Can circles always touch each other? Or can circles always intersect each other? Not necessarily. So suppose I have the Smith chart over here. This is my Smith chart. If this is my Smith chart and my stability circle is over here, let's go for the output stability case once. This circle indicates mod gamma in is equal to 1. Now, if mod S11 is less than 1, what would happen? If mod S11 is less than 1, any point in this Smith chart would be stable. But if S11 is now more than 1, there is not a single stable point inside the Smith chart. And that is disastrous. If mod S11 is less than 1. Else, if mod S11 is more than 1, no stable region exists. That is very sad. That means you cannot work with that MMIC, and that's a very bad design. Let us take a similar look for the input stability circle. Suppose this is the Smith chart. And the stability circle falls over here. This indicates mod gamma out equal to 1, this trajectory. This trajectory indicates just that. Now, what would happen is that if mod S22 is less than 1, then this larger area outside the stability circle inside the Smith chart would be stable. And this one would be stable if mod S22 is more than 1. Because this would indicate mod gamma out less than 1 in this case, and this would indicate mod gamma out less than 1 under this condition. So this is how you can use stability circles. Let us try to understand this with a small example. Suppose an MMIC is given to me. An MMIC amplifier having the following S parameters at 2 GHz. This is a value taken from a datasheet where the S11 is 0.65 with a phase of minus 95 degrees. S parameters are complex, never forget that. S12 is 0.035 with a phase of 40 degrees. S12 is small but not 0, so therefore it is not unilateral. S21 is the forward gain or the intrinsic gain, which is 5. It's a good thing, it's more than 1 with a phase of 115 degrees. And S22 is 0.8 with a phase of minus 35 degrees. Minus 35 degrees. Now, first thing that we have to see is this unconditionally stable or potentially unstable? Let's see how. Let's first do a stability test. Let's do the K delta test. So, delta is the system determinant, which is S11, S22 minus S12, S21. So, you can multiply this and find out the magnitude. And that is that comes out to be 0.5039. So delta is less than 1, which is a good thing. Let's now calculate K. K is 1 minus mod of S11 square minus mod of S22 square plus mod of delta square divided by 2 times mod of S12 S21. And I've already calculated this, and it comes out to be roughly about 0.547. It comes out to be 547. So what are we seeing? We are seeing that K is less than 1. Had K been more than 1, the transistor would have been unconditionally stable. So, but since K is less than 1, this indicates it's a potentially unstable amplifier. So now we have to be careful. We have to be careful and see whether the potential instability exists for the source side or the load side or both, or rather the input side or the output side. So therefore we have to construct the stability circle. So let's look at the output stability circle. The equation is mod gamma L minus CL is equal to RL, where CL has this formula S22 times delta times S11 conjugate, the whole conjugate divided by mod of S22 square minus delta square. Let's calculate and see what this gives us. So if you substitute the S parameter values, the center that we get is 0.8793 plus J 0.9632. This is in the rectangular or the Cartesian form. In the polar form, it is 1.304 with an angle of 48 degrees roughly. This is the value that I have gotten when I did the calculations. You can check it yourself. And the radius of the circle RL. This is the center of the circle. And RL is given as S12 times S21 divided by mod of S22 square minus mod delta square, the whole mod. And that comes out to be 0.4532. This is the radius of the circle. So we have got the center, we have got the radius of the output stability circle. Let's do the input stability circle. Where mod of gamma S minus Cs equals Rs. So what I see is that the center, now Cs, using the similar formula, S11 minus delta times S22 conjugate, whole conjugate divided by mod of S11 square minus mod of delta square. This comes out to be, I believe, minus 0.9389 plus J 1.5267, which is approximately 1.792 in the polar form with an angle of about 122 degrees. And the RS, this is the center, and the RS is S12 S21 divided by mod of S11 square minus mod gamma square whole mod, and this comes out to be about 1.0379. So therefore, let us look at the output stability circle, which sort of looks which would look something like realistic, which we will do on a Smith chart. So this is the Smith chart. Let us now see how to plot the CL first, that is the center of the circle. Now notice that if we are going to plot the output stability circle, that means we are on the gamma L plane. This is the origin, and we have to plot all the points with respect to gamma L coordinates. So therefore, the reflection coefficient magnitude is this distance on the bottom side of the Smith chart. This indicates mod gamma L equals 1. So let us take a scale and the radius, which is about 7.6 centimeters, corresponds to mod gamma L equal to 1. So if 7.6 corresponds to mod gamma of 1, then what would be the radius in centimeters for this 1.304? It's very easy to do that. All you have to do is multiply 7.6 into this quantity, 1.304. That comes out to be somewhere about 9.9 centimeters according to my calculations. And simultaneously, the angle is 48 degrees. So angle for gamma is always with respect to the right hand side axis. So angle of reflection coefficient 48 would be somewhere over here. So I'll take my scale and I'll mark the angle. And I will also mark the 9.9 centimeters from the origin of the Smith chart. So 9.9 is almost 10, and that comes out to be somewhere over here. So this point is my CL. What about RL? That's radius. So radius is 0.4532, but this is in terms of gamma axis. We have to convert this into centimeters. So therefore, again we will multiply 7.6 centimeter, the radius corresponding to 1, by this. So 7.6, when you multiply it with 0.4532, what you get is roughly about 3.4 centimeters. So what I will do, I will mark 3.4 centimeters starting from the CL as the origin or the center point of the circle. So 3.4 centimeters would be roughly somewhere over here. Now all that I have to do is take my compass, put the pin of the compass at the center and mark a radius equal to RL. And draw a part of the circle. The whole circle is not fully necessary. So this distance is actually RL, or I'll just mark this. It's a little easier to see. Now we have this circle which indicates mod gamma in equals 1. Now one side of the circle will indicate a stable region, one side will indicate unstable region. So which is which? Well, we have to see what is S11. S11 in magnitude, what we saw is 0.65. So S11 is less than 1. That means any point on this side over here, that is outside this circle, would be a stable region. So since it is little easier for me to mark an unstable region, I will show that this is unstable. So this is unstable for picking ZL. So apart from this region, any region inside the Smith chart, you can choose, or any point in this region of the Smith chart, you can choose as your gamma L, including the point which is matched, which is a matched node. Likewise, what you can do, you can take a Smith chart, you can plot what is CS, what is RS, and accordingly draw the circle. That will be a good exercise for you to see where the circle will lie and how much of the Smith chart it engulfs, if at all. So one thing we have proved over here is that definitely the circuit could be potentially unstable from the output side. Now input side also it could be potentially unstable, and that is for you to find out. I'll give you some hints to get started. What you can see is that the center of the Smith chart, the center of the input stability circle. So let me just mark this also. I'll call this as output stability circle. This one is the output stability circle. So the center for the input stability circle lies at an angle of 122 degrees. So if you look very carefully from here, 122 degrees would be over here. So if you take a scale and draw a line connecting the center of the Smith chart with this angle, the CS will lie anywhere over here. And since the value of CS in magnitude is more than 1, it will definitely lie outside the Smith chart. Maybe it will lie somewhere over here, that way to see. And then you can use RS, calculate both CS and RS magnitudes in centimeters, and then draw the proper circle. I leave that part to you as an exercise. So in today's lecture, we saw the significance of what is called as a stability circle. For an MMIC, there could be two stability circles, input stability circle and the output stability circle, corresponding to magnitudes of gamma in and gamma out. So when they intersect with the Smith chart, we have to choose. One region could be stable, the other region could be potentially unstable. And the choice of that has to be done by looking at the value of S11 in magnitude or the S22 in magnitude, whether you are doing for the input stability circle or the output stability circle. So we shall continue from this point onwards in the next lecture. Thank you.